Hi, I'm Keith Porter, Principal of SPA Risk LLC. This presentation is directed to the earthquake resilience community, that is, people who collaborate to help society to better resist earthquakes. This presentation is part of the FEMA-funded efforts by the National Institute of Building Sciences, an effort called Natural Hazard Mitigation Saves. In 2005, a large team organized by the Applied Technology Council under the management of the National Institute of Building Sciences produced this groundbreaking study for the Federal Emergency Management Agency. The study found that $3.5 billion in FEMA-funded public sector mitigation over the previous decade would ultimately save a present value of $14 billion in property repair costs, life safety impacts, avoided loss of functionality, and other future losses. $14 billion divided by $3.5 billion means that these particular mitigation measures produced a benefit-cost ratio of 4 to 1. That 2005 study examined only one category of natural hazard mitigation efforts. Here are some others: retrofit, adopting or exceeding codes, retrofit of utilities and transportation infrastructure, and changes to better resist wildland-urban interface fires. From 2017 to 2019, I helped to lead a team of many of the same experts and several new ones to update the 2005 study and close some of those gaps. The 2019 study probably represents the most extensive benefit-cost analysis of disaster mitigation ever performed. It didn't address everything, but it added greatly to our understanding of the nation's resilience investment gap and the savings that we can realize by trying to close that gap. This is our bottom line table. Columns show 5 approaches to disaster mitigation. Rows correspond to 5 perils that we considered. The cells show our estimated benefit-cost ratio for that combination of peril and mitigation method. For example, the red box shows that when you add up all the costs and benefits of 15 categories of seismic retrofit, the benefit-cost ratio is about 13 to 1. For each mitigation measure, we estimated the present value of avoided future losses in many categories. This pie chart shows how 6 leading benefit categories contribute to the 6 to 1 benefit cost ratio for federal grants when you sum over the perils. By 2019, the federal government and its partners had spent $27 billion on projects that would ultimately save an estimated $160 billion over their useful life, for a benefit cost ratio of 6 to 1. For most mitigation measures, we were able to map costs and benefits to identify the geographic locations where mitigation makes financial sense on a benefit-cost basis. Our benefits and costs only consider those places. The study ignores places where mitigation does not appear to be cost-effective on a benefit-cost ratio basis. We also examined cost and benefits by stakeholder, categorizing them in 5 groups: lenders, communities, which include governments and trading partners, the broader economy, tenants, owners, which includes lenders, and developers. This chart shows net benefit of optimal above code design for per year of new construction, where it makes sense to do so, and to the degree that satisfying engineering economic principles in cases with variable amounts of investment and monotonically decreasing slope of the curve of benefits versus costs. This picture generally describes the approach that we used and that most probabilistic risk analyses take to deal with categories of assets. You start on the left with available data about the assets you care about. Next, you distill that data into convenient engineering categories, and you might lump many assets together in small geographic groups, such as census tracts. We characterize the hazard to which each group is subjected, such as with the exceedance frequency of various levels of ground motion. We apply vulnerability models to the groups and calculate probabilistic loss. We can perform this analysis 2 or more times, once for current conditions and once assuming various remediation measures are performed. Then we can examine the difference to calculate useful quantities like the benefit-cost ratio. The 2019 study was peer-reviewed one way or another by 100 people from 70 organizations. We received and responded to 800 comments before publishing the report. That comment and response process greatly improved the study and helped to socialize it across the United States. Among the 5 approaches to mitigation, retrofit of existing buildings represents the biggest ticket effort, totaling $500 billion in cost, where the benefit cost ratio exceeds 1.0, and producing over $2 trillion in benefits if all the measures were undertaken where they're cost effective. Among 15 mitigation measures we examined were the seismic retrofit of manufactured housing using engineered tie-downs. Let me tell you about that particular part. Much of the manufactured housing stock rests on supports that lack resistance to lateral forces from earthquakes and winds. They commonly collapse in strong shaking. There are a few ways to reduce collapses, including engineered tie-downs, which appear to cost about half as much as the next more costly approach, earthquake-resistant bracing systems. To estimate the benefit-cost ratio of these engineered tie-down systems, we started by examining the performance of manufactured housing in the 1989 Loma Prieta earthquake. That was the first earthquake that offered sufficiently detailed and representative observations of ground motion and exposure and performance of manufactured homes. Here's the U.S. Geological Survey's map of shaking intensity in the epicentral region of the 1989 Loma Prieta earthquake. After the earthquake, the California Department of Housing and Urban Development surveyed 27 mobile home parks in the epicentral region. These parks contained 2,400 units, of which 590 collapsed. Most of the data could be geolocated to relate number of buildings, number of collapses, and estimated shaking. Here are those data tabulated by park. Each park can be represented by one dot on the chart. The x value of the dot is the estimated shaking in terms of peak ground velocity. The y value shows the fraction of homes that collapsed in that park. The red ovals show the x and y values for one park. We fit a curve to the data, driving the curve through a central point for mathematical reasons that I won't explain here. But the curve gives you an estimate of the average probability of collapse for an unrestrained manufactured home, given the level of peak ground velocity to which it's subjected. The California Department of Housing and Community Development performed a survey of repair cost data for collapsed homes, producing this pie chart of the sources of cost. The average monetary loss, inflated to 2018 dollars, totaled about $41,000 per housing unit. Collapses also lead to content losses, deaths, non-fatal medical injuries, non-fatal psychological injuries, displacement costs, and indirect economic losses. We added those to the property repair costs. In 2014, a few installers of engineered tie-down systems estimated the unit cost to install such a system at $1,000 to $2,000 per unit. Retrofit with an ETS is assumed to avoid most of the loss. If it avoids at least 9 out of 10 collapses, then on a first order basis, we can take benefits as equal to the present value of all the losses that would occur during the life of the property if you don't do a retrofit. That is to say, if the manufactured home is not secured against lateral motion. Now, fire matters to its victims, but it's a third order issue for the benefit cost analysis. We conservatively ignored the fire losses that are avoided if one installs an engineered tie-down system to manufactured housing in earthquake country. The benefit cost analysis involves a present value calculation that requires knowing how long the mitigation measure will last. In 2018, the California Department of Housing and Urban Development could not offer statistics about the life of an engineered tie-down system. One of its experts figured that outside a marine environment, an ETS might last as long as the home. A contractor thought maybe 15 to 20 years. We used a middle figure of 30 years, which the CDHCD expert thought was a reasonable average. Before 1989, few California manufactured homes had lateral bracing, but the fraction increased over the years. The 2017 American Community Survey from the U.S. Census Bureau recorded the fraction of homes that were anchored to their foundation in several metropolitan statistical areas. We used that data to estimate the fraction of anchored homes by state. Here are the first few rows of a table of those statistics. We integrated the seismic hazard, which again has to do with the frequency with which various levels of shaking occur, and the seismic vulnerability function for unanchored manufactured homes. The integral produces an estimate of the annualized loss for an unanchored home by census tract. We summed over census tract by county and calculated the present value of avoided loss. We also calculated the cost by county to retrofit all the unanchored homes. This map shows the ratio of avoided losses to cost, that is to say, the benefit cost ratio. In high hazard areas, the benefit cost ratio can reach 17 to 1. Where the map is white, the cost exceeds the expected present value of benefit. That's not to say that people shouldn't install an ETS in those places, only that long-run average savings are less than the cost. Census information suggests that there are 140,000 such units nationwide in the places where BCR exceeds 1.0. At $1,500 per unanchored unit, that equates with $210 million in cost. When you add up all the benefits in those places, you get $690 million in avoided future losses. The ratio of total societal benefit to total societal cost is 690 divided by 210, or about 3 to 1. We hope you find this information useful and that you'll use it to promote seismic resilience. If we can help you to do so, or if you have questions or advice, please contact me by phone, text, or email. Thanks very much.